Alright, welcome back to ME 3121. Today we're going to continue the discussion in chapter 14 on the gas vapor mixtures. So far you have already been probably noticing that we're primarily talking about mixture which is air in this case, and the mixture is just dry air and vapor. So that's going to be the focus of this chapter. And today we're going to continue the discussion and entering the topics of air conditioning process. So before we start talk about the air conditioning process, we need to discuss why we first create the air conditioner to start with. Your body is pretty much like a furnace. You consume energy, you eat, and then you burn the fuel, and then you generate heat. So you need to reject the heat to the surrounding to feel comfortable. So the temperature around you doesn't necessarily to be lower than your body temperature, because as we know that heat transfer happens as when you have a higher temperature and then it naturally goes to the lower temperature. So that happens. But on the other hand, what you have another mechanism is sweating. So if you sweat and then you got water out, the water is going to evaporate, and as water evaporates, it's going to absorb heat. It's going to absorb heat around it and from itself, and it's going to evaporate. So then it helps to cool your body temperature in that sense. So you need to make sure whatever surrounding environment you have, you need to make sure you can sweat comfortably. So that's how you feel comfortable. So here we said it's temperature. If the surrounding temperature is lower than your body temperature, it's easier for you to lose heat to the surrounding. And the relative humidity, we already know. If your surrounding humidity is really high, then it's going to be really hard for after you sweat for the water to evaporate into the air, because imagine it's already saturated, then the water the sweat you let go, it's not going to evaporate, so it's going to stuck there on your body, so you can no longer cool your body. And then, of course, air motion would help. So if there are a lot of air motion around, there's wind, and so it's going to keep changing your local environment. So it can bring maybe some fresh air and increase the heat transfer. Maybe bring a little bit more unsaturated air towards you, so you can keep letting go of the evaporation of your sweat. So that's why you need to drink water. If you stop drinking water, then sweating become harder. So that's why in the hot summer, you gotta make sure you are hydrated. On the other hand, if you don't want to cool your body, let's say the outside is pretty cold and you want to warm yourself up, otherwise you're going to lose heat to the surrounding too quickly. That's why you wear clothes to cover your skin to reduce the heat transfer. And for the part that's not covered, for example, your hands, on a cold winter day, your hands might also get cold. That's just your body is super smart. It cuts the circulation to lower your hands temperature, so therefore it also reduces the temperature gap between your hand to the surrounding air. So from that, the heat transfer is going to be less efficient, right? So we've been keep talking about you need the temperature gradient, or the bigger the temperature difference there is, the better the heat transfer is. So if you lower your temperature to the surrounding temperature, then the heat transfer can stop. So that's just your body being very smart to help you keep losing heat to the surrounding. So now you know when your body will feel comfortable. So there are already a lot of people want to feel comfortable, so they developed these machine that we call air conditioner. So let's take a look the major air conditioning process. There's just simple heating, simple cooling, which is pretty much literal. You can understand. You just add heat up or just cool it down. Or you can just add moisture or dehumidifying, remove moisture. So there are four basic process, and of course you can imagine you can combine them together. On the right hand side there's the psychometric chart where you can see simple heating or simple cooling. You are going to keep the humidity the same, right? So remember the vertical axis is omega, the absolute humidity. If you're just simply heating it up, temperature increase, then omega doesn't change. On the other hand, if you just humidifying or dehumidifying, you are only going to increase omega or decrease omega. And then you can combine them together, say heating and humidifying. And so both the temperature are going to increase and omega going to increase. So that's when you want to keep your room warm. But if you want to cool it out, you can go to the other direction. So these are the basic process for what an air conditioner can do. Let's look at how we can analyze it mathematically. So here's the analysis for the air conditioning process. We look into the mass balance and the energy balance. For mass balance, we can separate into dry air. So the dry air will stay constant. The mass flow of dry air would be in equals to out, and same as water, in equals to out. So for the mass balance, we usually separate the dry air and the water. And then you can write out the energy balance, and that is E in dot equals to E out dot, because we treat it as a steady flow. And there are pretty much three components for the energy. That is heat transfer, work, and the enthalpy carried by the mass. And usually in air conditioning, the only work that involves is a fan work. So that would be usually quite small compared to the heat transfer. So a lot of time we do not really consider that term. So with this, we can start to analyze some typical problems. And today we're going to look at about 6 examples. So let's go through them one by one. The first one is just simple heating or cooling. Notice here omega is constant during the simple heating and cooling, and on the psychometry chart is just a flat line. So please keep that in mind. Make sure you know how to draw these process line as well. So in the simple cooling, the mass content doesn't change, humidity doesn't change, and you can write out the energy balance. There's no work, only heat transfer, and that equals to the enthalpy change across these whatever heat transfer foil, whether it's losing heat or gaining heat. So let's take a look at of this example. So the problem gives you the inlet air, and it says it's cooled at constant pressure to dew point temperature, and determine how much heat it lost through this process. Now pretty much if you want to find out Q, will equals to H2 minus H1 in this case. So we just, we're given the inlet state, we can determine H1 from the chart or from calculation. Then we just need to find out H2. So we're told that the final temperature is at dew point temperature. So how we're going to find out the dew point temperature? Remember, this process is just a simple cooling process, so omega stayed the same. So on your chart, you will draw a flat line to find the dew temperature. And remember, the dew temperature is that if the temperature is lower than that temperature, water is going to condense. So that's how you get phi equals to 1. So the relative humidity is 1. Okay, so the problem didn't really explicitly say the exit humidity is 100%, but from the statement in the problem, you can derive that. So let's take a look at the chart. This is in English unit, so make sure you find out the proper table in the appendix. State 1 is 100 Fahrenheit, and the 70% relative humidity. So you're going to draw this line straight up and to see where they met. So they about almost meet on the top. And then from there you can read the H1. So the H line is here, BTU per pound. There's 50, 55, and 60 here. So 55, 56, 57. So my state 1, H is between 56 and 57. So let's just, it's close to 57. So from the chart, we read H1 equals to 56.7 BTU per pound mass. And now we need to find out H2. Remember we said omega doesn't change. So it will be a flat line. And it reached to the saturation point, or it reached to the dew point temperature. We're interested in H, so we can read H directly from there. So again, this is 50, 51, 52, 53, 54. So it's between 53 and 54. So let's just call it H2 equals to 53.8. And then you can calculate Q. In this case, H2 minus H1 is a negative number. So negative 2.9 BTU per pound mass of dry air. Yeah, we got to be a little explicit in this case. So here is dry air and dry air. And so this will be Q out. So if the question asks you what is the dew point, you got to make sure you know how to find it out. Again, I like to just go from the 100% point directly, go down to read the dry temperature. So let's see that. So looks like it's between 85 and 90. It's closer to 90. Let's call it dew point is about 87. Let's say 87.5 Fahrenheit. So how much it get cooled? It get cooled from 100 to 87, so about 13 Fahrenheit. Okay, now let's look at the second scenario where you have heating with humidification. So usually this is done in two steps. you have air first passing through a simple heating, so you just go through heating coil, and after that the temperature reach to your desired temperature, and then it goes through a humidifying, so you add water or add moisture into these air. So it's shown on the left bottom corner. So as you can see, you have two steps. So from 1 to 2, omega doesn't change, it's just simple heating. And then from 2 to 3, you start to add water to it. So again, from this, you can write out the mass balance. The dry air never changed from 1 to 2 to 3. The dry air remained the same. But for water, 1 to 2, omega doesn't change. But 2 to 3, omega actually does change where you add water. So the m dot water equals to the difference between omega 3 and omega 2. For energy balance, the energy balance at the heating, so you have a Q in equals to, again, so m dot H2 minus H1, just like what we did earlier. So let's take a look how we do the analysis with some numbers. So you're given the inlet property of the air, and you're given the volumetric flow rate. Then you condition to 25 Celsius and 60% humidity, which is the exit, so T3 and V3 is given. And you're told that the air is first heated to 22. So the first step is 22 Celsius. The question asks you for the heat supply in the heating process from 1 to 2 and the mass flow rate of the steam adding, so from 2 to 3. So to find the heating, so Q equals to H2 minus H1, right? And then if you want to find the total Q in, would be m dot A times H2 minus H1. So we need to find out the mass flow rate of the dry air. And of course find H2 and H1. So H1 is given pretty much, and H2 you can find it out because from H1 to H2 omega doesn't change. So you can find out H2 in that case. So how do we find out mass flow rate of the dry air? We are given the mass flow rate of the volumetric flow rate of the dry air at the inlet, and volumetric flow rate is defined as mass flow rate times specific volume. So from there, we can actually find out the mass flow rate. So let's go to the chart and collect some numbers. So for state 1, we have 10 degrees Celsius and 30% relative humidity. So 10 degree and 30. So it's here. And you can read the H from there. So you can pretty much say, so here's 20, and each grid is 1, so 19, 18, 17, 16. So each one is 16. We also need to find out the V1. Remember, we need the V1 to calculate the mass flow rate. So remember, V1 is parallel to these green lines. So it's about that. This one is 0.8. This one is 0.81. So that point looks like right in the middle. So we call it 0.805. So let's write those things down. So from the chart, you find out H1 equals to 16 kilojoule per kilogram of dry air. V1 equals to 0.805 meter cube per kilogram dry air. Then we can look up for point 2. We said point 2 is 22 Celsius. Omega equals to omega 1, which means it is a flat line. So you can draw a flat line from point 1 and cross it with 22. So this is 22. And we need H, so go to read H. It looks like 28. So 30, 29, so about 28. So we find out H2 is 28 kilojoule per kilogram dry air. Now we can calculate MA dot, which is V1 flow rate over specific volume V1. So 45 meter cube per minute divided by 0.805 meter cube per kilogram. So you got 55.9 kilogram dry air per minute. Then we can calculate Q in equals to m dot times H2 minus H1, plug in number, I'm going to skip a little bit, equals to 670.8 kilojoule per minute. You can convert the unit into second, but it doesn't say you have to, so you don't have to. And the next part asks you how much water you need to add in during the humidification section. So from the mass balance, we know that m dot V2 from the vapor content from 2 to 3, that's the adding water part. So m dot V2 plus the mass of the steam adding in equals to the final water content. And we know that the moisture in state 2 equals to state 1. So this equals to V1, which you can express as omega 1 times m dot A plus steam equals to omega 3 m dot A. So that means we already found m dot A. We need to find omega 1 and omega 3. So earlier we didn't read omega 1, so let's read that first. So from here you can draw this line all the way to the right. So let's see, this is 2 and this is 3. This is close to 2.5, so let's just call it 2.5. Earlier we can write one more here. Omega 1 equals to, remember this is in gram, but our ratio is actually kilograms, so it's a 0.0025 kilogram per kilogram dry air. And then let's see omega 3. You're given the state 3, temperature is 25 and humidity is 60%. So read the chart one more time. 25, humidity is 60%. And that looks like 12, so 0.0112. All right, now we can calculate the steam. M dot steam equals to M dot A times omega 3 minus omega 1. We know all the numbers. I'm going to skip the plugging in again. It's 0.53 kilogram per minute. Similarly, we can do the cooling with dehumidification. The concept is pretty similar to the previous one, so we're going to go a little bit quicker on this one. So you can see from the psychrometric chart on the right, at the beginning you have air start to cool off. And as it cools off, at one point it becomes saturated. And when it becomes saturated, water is going to come out, and then you start to remove the water out of the air conditioning system, and then the process will remain on these 100% relative humidity line. So in this process, as illustrated on this chart on the bottom, you can see, so you have air coming in, and then there will be just an outlet for the condensation water to leave the system. Again, mass would be dry air mass doesn't change, and water mass would be in is at inlet 1 equals to water goes out from 2 and from the condensation. So you can calculate the condensation amount of water. Energy balance, we really just have, we actually have 3 inlet and outlet, and there's also Q leaving out of this system as well. So energy coming in is m dot 1 times h1, and equals to out, we have Q plus all the 2 outlet in this case. So we can calculate how much heat transfer it happens during this process. So this problem is pretty similar to the previous heating with humidification, so we're going to just go really quickly. You're welcome to just pause this video and try to solve this problem yourself. The concept is pretty much similar. You're given the condition at state 1, and you're also given the volumetric flow rate at state 1, so you know you need to you will need to look up for the specific volume to calculate mass flow rate. And you know after it leaves, it becomes saturated. So that means during this process, there will be water condense, and there is an outlet for the condensed water to leave the system. So the question asks you, what is the heat transfer going out, and how much water got moved out? So to calculate m dot out, you will still do m dot A times H2 minus H1. That's how much the air cooled, and the energy associated with it drops as well. Also in this case, we need to have the water energy removed from system as well. So you do need to look up actually to find out the m dot water first before you calculate Q out. And the m dot water from the earlier page, we already know that's just water condensation from it. So m dot water equals to m dot A times omega 1, which is a bit more water, minus omega 2, which has less water. So we need to calculate m dot A. We can find out omega 1 and omega 2 from the 2 state given. So that's pretty much it. Once you have that, you read H1, omega 1, and V1. From the second point, you read also H2 and omega 2. Then you can calculate m dot water leaving the system. Then you can plug into the energy equation. You just need to find out HF in that sense. And so you go to the water table to find out water leaving. So you're told water leaving at 14 degrees Celsius. So you can find HF at 14 degrees Celsius to approximate the enthalpy of the water leaving the system. So first state, 30 degrees Celsius and 80% humidity. It's about this point. And then you go ahead and read the H on the top and omega on the right. So H is about, so this is 80, 81, 1, 2, 3, 4, 5. So between 85 and 86, we can call it 85.5 if you want. And omega on the right hand side, so this is 20, this is 21, so this is over 21.5, so we can say it's 21.6, and then we can read the volume, which is parallel to that line, so 0.88, so this line would be 0.89. My specific volume would be between those two numbers. We can call it 0.888 or 89. So let's write them out. Omega 1 equals to 0.0216. And V1 equals to 0.889. H1 is 85.5. Similarly, you can do it for point 2, the outlet, which is 14 degrees Celsius and 100%. Then you can read the H and omega accordingly. H is about 39.5 and omega is about 0.01. So I'm going to skip writing them. You can do this by yourself. And then from there you can calculate m dot A equals to V1 dot over V1 specific volume, and you can calculate m dot water removed equals to m dot A times omega 1 minus omega 2, and Q out equals to m dot A times H1 minus H2 minus m dot water times H water. So we need to look up in the water table. So the water table here, you have 15 and 10. Our temperature is 14 degrees Celsius. So my H is between 42 and 62. You got to do a little interpolation and you will find out H of water equals to 58.8. Then you can plug back into this Q equation and calculate the number. So I would encourage you to go ahead and try it out yourself. One thing I do want to point out is this process would go through a cooling. So the humidity, the specific humidity doesn't change at the beginning. So it would just be a flat line to the left. It starts to cool. But once it hits the saturation line, the water is going to leave from the air and it starts to condensate. And then the air will remain as a saturated air. So it will follow the saturation line like that. So that's the process line. The next example is called evaporative cooling. Basically what it happens is you probably had this experience where you say feel really hot and you put some wet towel on your head. So the wet towel is going to evaporate water into the air, and then you can feel immediately cooling on your head. Or another scenario is if you ever wear clothes and jump into the water, or you just happen to get caught in the rain, you will feel very cold because the water of the wet clothes will start to draw heat from your body. And especially, when there's air passing through you, and that's when the air is going to draw more water to evaporate, and it's going to draw more heat from you. So that's pretty much the evaporative cooling. If you recall, this process is pretty much similar as when we discussed the wet bulb process and how we find out the wet bulb temperature. So this process is very much like a adiabatic saturation process. So as shown in the top right corner, so this process is pretty much like that. Of course, it's not 100%, but it's close enough. So we're going to say during this process that the H of the air does not change because it is an adiabatic saturation process. And if H doesn't change, then wet bulb temperature doesn't change. So if you recall on the psychometry chart, these two lines are parallel to each other, more or less. And of course, the lowest the temperature it can be is when it cooled down to saturation. So on the 2', that would be the lowest the temperature this process can reach. So you do have a limit of this process. So for example, this desert dweller situation where they put soaked cloths on top of their head to help them to cool down. And in the desert, your given temperature is 120 Fahrenheit and humidity is only 10%. And they ask you what is the possible lowest temperature of this cloth. So that's when the local surrounding air to be saturated. And that's the lowest the temperature it can be. So that pretty much means you go to the psychometry chart, find out your state 1 is 120. It's right at the edge, and humidity is only 10%, so you're here. And you're going to follow this constant wet bulb temperature line, and once it hit to saturation, that is the lowest the temperature it is able to get. You can read from this graph, like this is saturation temperature 70, so this would be 71, 72, 73, 74, so it's between 73 to 74, or you go down to read the dry bulb temperature, which I like more. So you can tell this is pretty much to 74. The minimum temperature it can reach is roughly the wet bulb temperature for this case, and that is about 74 Fahrenheit. The next topic is the adiabatic mixing of airstream situation. So this is when you have say the building AC system, instead of just letting these air circulating, you want to bring in some fresh air so you can keep the air circulating, and which is probably better for your health. So in this case, if you look at the chart on the right, you have the air coming in, and then let's say inlet 2 is some fresh air. So the old air will mix with the fresh air and then become the new air going through the building again. And we assume this process is adiabatic, so the mixing region, we assume it's a small region, and there's no heat transfer during this mixing process. And then we can figure out the relations between the relations during this process, we have the air of mass of air that inlet add together equal to outlet, and water vapor, the summation of the inlet equals to the outlet, energy coming in equals to the energy goes out. And from these three equations, you can work out a formula to calculate whatever you need. You can find out the ratio of A1 and A2. You can, if you know the ratio, you can find out maybe omega 1 or omega 2. So you can draw this chart on the psychometry chart as well to see that 1 add 2, they mix equals to 3, and 3, how do you define 3 is where you find omega 3 and H3, so you can determine the point 3 where it locates. So let's look at an example. So you're given inlet property and outlet property. You're asked to find out all the outlet property. And from the earlier page, we already know if we can determine omega 3 and H3, then we can decide all the rest property of state 3. And to find out omega 3 and H3, look at the equation on the left. We need to find out m dot A1, m dot A2, the mass flow rate of the two inlets ratio, and omega 1 to H12. But if we're given the state other properties, so we can easily find out. So once we fix the state 3, we can from there to use the mass ratio to calculate the total mass in 3 and to find out the volumetric flow rate in 3. So let's take a look. So first of all, locate state 1 and state 2. State 1, 14 degrees Celsius and 100% humidity. State 2, 32 degree and 60% humidity. From there, we can go ahead and read H1, V1, omega 1, H2, V2, omega 2. So I'm not going to read in details. Hopefully you can find out by yourself by now. So from the chart, we locate these numbers. We were given the volumetric flow rate at both inlet. We can then find out the m dot A1 and m dot A2. You can quickly do the process. We already did that before. Just use volumetric flow rate divided by specific volume. And then we can calculate m dot A3 equals to in, add together, which is 83 kilogram per minute. And from the previous ratio formula, we know m dot A1 over m dot A2 equals to omega 2 minus omega 3 divided by omega 3 minus omega 1. So you can plug in number. We found out A1 and A2. Omega 1, omega 2 already know, so we can calculate omega 3. Which is 0.0122 kilogram per kilogram dry air. And similarly, you can find out, so this ratio also equals to H2 minus H3 over H3 minus H1. So you find out H3 is 50.8 kilojoule per kilogram dry air. Then you can go back to the chart and read off. So that point should be on the connection line between A1 and 2. So omega 3, 0.0122, so it's 12.2. 12 is here. This is 12.5, so it's in the middle. So let's try to draw a flat line. And then H is 50.8 0.8, which is close to 51. This is 51, so hopefully these two lines will cross on the connection between point 1 and 2. So now we locate the state 3. We can from there to read the other properties, and so we can see that the relative humidity is close to 90%. We can say this is maybe 89 or 88. And it asks a dry bulb temperature, so you just draw a straight line going down. It's pretty close to 19 degrees Celsius, so we can say it's 19. And then they ask you to calculate the volumetric flow rate for the mixing after the two-stream mixed. So that means we need to find the specific volume at state 3. So specific volume between 0.84 and 0.85. So it's almost in the middle. We can say it's 0.845. Then you can calculate V3 equals to m dot A3 times V3, and you get approximately 70.1 meter cube per minute. So last application of this section is the wet cooling towers. You probably remember that when we discussed the Rankine cycle, we talked about the power plant, and there you need to have the cooling system where the steam will condense. And there you need a big reservoir to cool down the hot water, especially if the capacity of the power plant is huge, and so you will need a big capacity of cooling reservoir. So sometimes it's just not feasible. You just dump the heat into, say, lake next to you. Sometimes you don't even have a lake next to you. Sometimes the lake is too sensitive to the heat rejection. There are a lot of water creatures there. You don't really want to destroy the environment there, so that's when a cooling tower is come in handy. You probably have seen this type of cooling tower. There's an illustration on the right to show. This is a really tall stack, and there's some warm water coming in, and it sprays through, and there will be heat exchange between the warm water and the air. And then some water will cool off during this heat exchange, and the water will start to condense into the liquid format. And then you take out the liquid format as liquid, and then it continue combine with more water to keep cooling whatever your Rankine cycle or some other cycles that you want to cool off. And then the hot air will rise up and will leave this stack. So you probably have seen those type of stacks somewhere. It looks more like this, and a lot of time you see there are a lot of steam coming out, and that's when it's running. So those steams are just some hot, humid air. And these just show you, instead of using a cooling tower, you can also have a spray pound. If the location allowed, you can just let the warm water spray directly into the open atmosphere, and as it condenses, it just fall into the pond below. And then lastly, if you have the facility where you have your hot water and just dump into this pond, and it just going to have heat exchange directly with the open atmosphere. So let's do a quick calculation about this cooling tower. So first, the problem says the water leaves the condenser of the power plant. Remember, we need to, in the condenser, the steam need to cool off, and then the cooling water become warm. So it entered this cooling tower because you want to keep that cooling water cool. So this side also kind of running a cycle. So it enters as 35 degrees C, and you're given the mass flow rate, and it is cooled. When it leaves, it becomes 22 degrees C. And air coming in, air is 20 degrees Celsius and 60% humidity. And when it leaves, the air leaves at 30 degrees Celsius and 100% humidity. And neglect the power input by the fan. Like we said before, fan work is relatively small compared to the heat. And find out the volumetric flow rate of air going into the cooling tower. So let's give it some numbers. So let's call this inlet 1 and outlet 2 for air. And for water, inlet we call it 3 and outlet we call it 4. So we're asked to find out volumetric flow rate 1 and the mass flow rate of the required make-up water. So what is make-up water? So here's the thing. You can imagine air starts with unsaturated and leave with saturated, so it will take away some vapor. So this is my cooling water here at 3. So that means when it leaves as 4, the water got less. But remember, this water is going to cool off your power cycle. So if you have less water and less, then eventually you can think of the extreme case where you just have no water. So how can you cool the power plant cycle? So you have to keep adding some makeup water to fit in to continue cool the power plant. So here's the makeup. You can imagine makeup is just to make up the mass difference between 3 and 4. So basically you need to find out m dot 3 minus m dot 4 in that sense. Also, let's not forget we're actually given the flow rate of m dot 3 equals to 100 kilogram per second. So that's going to be helpful. So we're probably going to use all 3 equations, mass and energy, to link all the mass m dot A, m dot 3, and m dot 4 together. So let's take a look. For mass equation, we have air, m dot A1 equals to m dot A2 equals to m dot A. We have water. So water has, so remember air also have water content. So that would be m dot A1 omega 1 plus m dot 3 equals to m dot A2 omega 2 plus m dot 4. So the m dot A1 and m dot A2, we can pretty much just use m dot A. Then we can write out the energy equation, which is inlet m dot A times H1 plus m dot 3 H3 equals to m dot A H2 plus m dot 4 H4. So we have, I'm already pretty much plugging in this equation. So we have 1 equation and 2 equation. Remember, m dot 3 is a known number, so I just don't know m dot 4 and m dot A. 2 unknown, 2 equations, I can solve it. It's a little tedious, so let's see how we can rearrange things to cancel out 1 unknown. So from equation 1, maybe let's substitute m dot 4 first. So m dot 4 equals to m dot 3 minus m dot A omega 2 minus omega 1. Then you can plug in to equation 2. So plug in this into m dot 4. We got m dot AH1 plus m dot 3H3 equals to m dot AH2 plus m dot 3 minus m dot A omega 2 minus omega 1 times H4. So it looks like this is going to be just one formula in terms of m dot A. So you can rearrange everything. Go ahead and do this by yourself. M dot A equals to m dot 3 H3 minus H4 divided by H2 minus H1 minus omega 2 minus omega 1 times H3. So you can read omega 1, 2, H1, 2 on the chart. H3 and H4 you can read from the table A4. So H3 is 35. So you can take HF at 35 degree and H4 is at 22, so you have to interpolate between these two numbers. You got H3 equals to 146.64 and H4 equals to 92.28. So from this psychometry chart, hopefully you can read all the numbers by yourself now. H1 equals to 42.2, omega 1 equals to 0.0087, V1 equals to 0.842, H2 equals to 100 kilojoule per kilogram, and omega 2 equals to 0.0273 kilogram per kilogram dry air. Then we can plug into this m dot A formula. You get 96.9 kilogram per second. You're asked to calculate the volumetric flow rate at inlet of air. So it would be m dot A times V1. That gives you 81.6 meter cube per second. To calculate the makeup water, that equals to m dot 3 minus m dot 4, which is, you can use equation 1, m dot A times omega 2 minus omega 1, which is 1.8 kilogram per second. So this way I don't need to calculate m dot 4 again. So that's pretty much it. Conclude all the examples in this chapter. Notice here we're pretty much just heavily rely on reading the psychometry chart once we're sure that we're able to use that 1 atmosphere pressure. So hopefully now you feel very comfortable reading the chart and setting up the equations, pretty much just mass equations and energy equations. So hopefully you got enough practice today, and that concludes chapter 14. And next time we'll start a new chapter. So see you next time.